Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll continue this lecture tutorial on simple molecules and covalent bonds. So on top of what we have covered in the previous lecture tutorials or lectorials, we have talked about bonding. We have talked about interatomic bondings, meaning to say bonds formed between the two different atoms, which it can be between ions. Then you can get ionic bonding, and then you will also talk about between the same metal atoms. Then you will get metallic bonding, and in this particular case we will specifically talk about between the non-metal atoms, and between the non-metal atoms they don't like to form ionic or covalent bonding, so instead they don't like to form ionic or metallic bonding, so they instead will form covalent bond. All right, so in terms of the Cambridge curriculum for the 2023 examination series, they specifically state that candidates should be able to basically define what a covalent bond is. This is the process, so you need to be very careful. The process is not the same as the definition. Okay, so this means does not equal. So it's an equal with a line across it, means does not equal. All right, so a lot of students, when someone asks them what is a covalent bond, they will say a covalent bond is sharing of electron. A covalent bond is when a pair of electrons is shared, and the process itself does not define the bond itself, and that's something I'll cover in a few minutes from now. Okay, so the next bit is also saying describe the formation. Describe can be in words, can also be in picture. Okay, the picture here refers to dot and cross, not like a drawing, not like an artistic kind of drawing, of course, but it's also in words in terms of how many electrons are being shared, and therefore can you count covalent bonds or not. All right, unlike in the previous bit when we did ionic compounds, so ionic bond is a force field and you cannot count ionic bonds, so they are uncountable, but covalent bond is directional, so you can count them. All right, so we'll apply to these particular case studies: hydrogen, chlorine, water, methane, CH4, ammonia, NH3, hydrogen chloride, HCl, methanol, CH3OH, ethene, C2H4, oxygen, carbon dioxide, and also nitrogen. And you have to use the dot and cross to show the electronic configurations in these, and then importantly, and similar molecules. So just because these are in the syllabus doesn't mean that they cannot ask you any other thing, because they say and similar molecules, and this is the dangerous bit, because students always just think I just need to know this, but if you know this, you should be able to apply them to similar molecules. Lastly, just like for ionic compounds, we always talk about structure and bonding. What are the kind of properties we can associate with the structure and bonding? So simple molecular compounds have simple molecular structure. What are we breaking? We are only breaking the weak intermolecular forces for simple molecules. So that means if you don't know your syllabus, then you don't really know what you are breaking, and therefore you won't be able to associate the law melting and boiling points of simple molecular compounds. They also do not conduct electricity, unlike ionic compounds, which can conduct in aqueous or molten state, but not in solid state. Simple covalent molecules just simply do not conduct, even when they are solid, liquid, or gas, or even in aqueous solution is debatable, and we will see in a couple of examples later on, but whether they are solid, liquid, or gas, they simply do not conduct. To kick off, just like to define it. So this is a proper definition, and the definition itself is not the process. It involves we talking about electrostatic force attraction between the two neighboring nuclei for a localized pair of bonding electrons shared between them. So if, for example, if I have hydrogen has a nucleus, the nucleus has a protons, and I'll share with another hydrogen which also has a protons. The protons in the nucleus is positively charged, and I'll have the electron and the electron there. The electrons are negatively charged. These electrons are attracted to both this nuclei and this nuclei because they are protons. They are attracted to the negative charge. So the force attraction between the two positively charged nuclei due to the protons in the nucleus of an atom with the bonding electrons. So the electrons used to be orbiting freely in electron shell, but now they are localized. Localized means they are no longer delocalized, no longer moving freely. They are localized, they are fixed in between, okay, in between. In fact, they are held in between the two nuclei due to the attraction between the two positively charged nuclei with the bonding electrons that are now localized between them. So in all levels, simply we form covalent bonds in order to achieve noble gas electronic configuration, and that is an oversimplification. This is an oversimplification, and that is not always necessarily the case as you progress to advanced level chemistry. If you draw the display formula, we would draw this as display because this is a simple molecule, so we can draw it as a covalent bond like this. But be aware that just because we draw a line does not always mean it's a covalent bond. You need to think, is it between non-metal atom or is it between ions? So be very careful. These are two non-metal atoms. They share electrons that form covalent bond. So one single covalent bond represents two bonding electrons being shared. One covalent bond between the two atoms represent one electron from this, one electron from that. This is a single covalent bond. It has two bonding electrons. So this is a single covalent bond is equal to two bonding electrons. All right. So if we look at periodic table, which you know carbon is in group 4, it's got 4 outer shell electrons. In order to achieve the noble gas electronic configuration, it will share 4 more electrons. It needs 4 more electrons because 4 plus 4 will give you 8. So altogether, you need 4 more plus the 4 that you already have around the carbon for the carbon to have noble gas electronic configuration. So this one, group 5, will need 3 more electrons for sharing, and so on and so forth. So that one need 2 more. And this group 7, remember that when you're in group 7, you would like to form ions, but only when you have metal atom that can lose electrons to you. But when you have your non-metal with another non-metal, then there isn't really that preference for you to form ions. Instead, you will share electrons. So you got to think about what makes an ionic compound and what makes a covalent compound, okay? So you need 1 more electron, which of course, when you talk about the reaction with a metal, then the metal will lose electrons to the non-metals, but between the non-metal and the non-metal, they will just share electron with each other, and you will need to share 1 electrons for you to go to 7 plus 1, which is 8 valence electrons. So dot and cross diagram shows how the valence electrons are arranged, and Lewis diagram. So this guy named Lewis, I think it's Gilbert Lewis, he won a Nobel Prize back in the 1930s for his work in simplifying this concept of bonding and making it easier for people to appreciate and understand chemical bonding. So he did a lot of good work on that. When we draw 1 line, as I had drawn for hydrogen here, it represents single covalent bond. When we draw 2 lines, it represents double bond, 3 lines represent triple bond, and so on and so forth. This is slightly important, and in a couple examples later on, I should hopefully show you that we need to appreciate that the second period element can only fill up the second electronic shell, and that means maximum 8 electrons in the outer shell only. Okay. However, when you go to third period elements, third period elements can have up to 18 electrons maximum. All right. So I know in the periodic table you fill from sodium, magnesium, that is the third period, all the way to argon, and after argon you fill the 4th period, which is potassium and calcium, and then after that 10 elements from scandium to titanium, even though it looks like it's in the 4th row, but actually is part of the 3rd electron shell, and there are 10 elements in there. Okay, so 2 plus 8 plus 10. This is the transition metal series. This is the first row of the transition metal series, which is actually part of the third shell, but you fill the fourth you fill potassium and calcium across the fourth shell first before you continue filling in this bit of the third shell. Okay, and it will make more sense when you go to A-level chemistry. Okay, so this is sodium, magnesium, and this is 2 plus 6 plus 10, and this is going from aluminium all the way to argon. So altogether 18 electrons maximum in the third shell, and is only true for the second shell element, that you can only have up to 8 electrons in the valence shell, because 2 plus 6 without this one is just 8 electrons. Now these are just a couple of dot and cross to kind of introduce you the idea. So hydrogen has one valence electron. That is very important. Hydrogen is the first element in the periodic table, so the atom has one valence electron to balance the one proton in the nucleus. All right, so one electron and one electron, they share, and this hydrogen now has 2 electrons in its valence shell. This hydrogen has 2 electrons in its valence shell. They both obtain fully filled outer shell, because the outer shell is just the first shell, and it can only come up to 2 electrons in the first shell. Okay, so this is a single bond. I do not draw any lone pair because there's no non-bonding electrons. I kept on saying lone pair. Lone pair is equal to 2 non-bonding electrons. So one lone pair equal to 2 non-bonding electrons, and there are no electrons that are not used for bonding, because the hydrogen uses all the electrons for bonding there. Single covalent bond. One single covalent bond means 2 bonding electrons. So what can we say about oxygen? So this oxygen is from group 6. It's got 2, 4, 6 electrons in the valence shell. So be careful that oxygen has is element number 8 in the periodic table. So the electronic configuration of the atom is actually 2, 6 and 2, 6. However, when we draw the dot and cross, typically questions will ask us to draw only the valence shell, but this is not always the case. So make sure you always read, is it draw the valence shell electron only, or is it draw all of them? Okay, so if there is 6 valence electrons and you want to reach to a noble gas configuration, the closest noble gas to you would be filling this up to 8 in the second shell. That means you will bring it up to neon's electronic configuration, and therefore 6 plus 2 will give you 8. The same thing happens to the other oxygen atom. You want to go to noble gas configuration, the closest you will be is to get to 8, that is to gain 2 electrons. However, this is not bonding between metal and non-metal. This is bonding between 2 non-metal atoms, so they prefer to share electrons, and therefore the same concept applies. By sharing, they need to share 2 extra electrons from the other atom. Okay, and hence here you see 1 cross, 1 dot, that is sharing 1 for this one, and this one is being shared to the other one. And you have another dot and cross, so this represents 2 lines because there are 4 bonding electrons. One line represents 1 covalent bond, meaning 1 electron from this atom, 1 electron from this atom. The other line represents another covalent bond, that is 1 electron from this atom and 1 electron from the other atom. So altogether, when we show 2 lines, that represent a double covalent bond. So this is a double covalent bond, but be very careful. Later on we'll deal with water molecule. Water molecule, the oxygen forms 2 single covalent bonds. 2 single covalent bond also means the oxygen share 2 of its 6 valence electrons for covalent bonding. So because you also form 2 covalent bond, here also form 2 covalent bond, except here is 2 times single, here is 1 time double. So be very careful on that. All right, and in fact that's what I was just talking about, the dot and cross for water, as well as all these other things that are within the syllabus as well. So chlorine gas, CO2, you should be aware that chlorine gas, chlorine just like hydrogen, you can draw like this. but this is how you draw the display formula. But do not forget that hydrogen is in group 1, whereas chlorine is in group 7. So it's got 7 valence electrons. So when you use it for bonding, you only use 1 out of 7 for bonding. That means you're left with 3 lone pairs on the chlorine, such that when you draw the dot and cross, a lot of students will forget that there are actually other electrons that are not used for bonding in the outer shell because they forgot the most basic thing about periodic table, which is group number tells you how many valence electrons there are. However, for hydrogen, it uses the one and only electrons in the first shell for forming covalent bond. It doesn't have any non-bonding electrons, unlike the group 17 element there. So the best representation of this is shown in this contrast when you form hydrogen halide. So this is called hydrogen chloride, but you can also get hydrogen fluoride with the IDE. Of course, you can also get hydrogen bromide with an IDE as well, and hydrogen iodide as well, okay, and so on and so forth. So altogether, these are called hydrogen halide, and this will make more sense when we come to naming of compound. All right, the halide refers to the element no longer being the atom itself when it's bonded to something else. All right, so here in the dot and cross, you see the non-bonding electrons on the chlorine because it only uses 1 out of the 7 valence electron for bonding, and hydrogen uses the one and only electron in its first and only shell that is filled with electrons for forming covalent bond, and therefore no other non-bonding electrons there. This is how I would write first of all, because it's easy to count. Hydrogen forms single covalent bond, chlorine forms single covalent bond in order to go from 7 outer shell electrons, 7 plus 1, whereas the other hydrogen is 1 plus 1 because in the first shell you only accommodate 2 electron maximum. The same deal with the water molecule down here, OH2, 2 single covalent bond because the oxygen forms 2 covalent bonds. It can be 1 double bond like this one double bond, or it can be 2 single bond, and if you draw like that, and then the hydrogen is 1 plus 1 electron on the hydrogen, and you just form 1 extra covalent bond. So the one that I underline represents how many extra covalent bond does it form. When it forms, therefore oxygen form 2 covalent bond usually, hydrogen form 1 covalent bond usually. Nitrogen is in group 5, so it's got 5 outer shell electrons. 1, 2, 3, 4, 5. Look at the cross. 1, 2, 3, 4, 5. Hydrogen is in group 1, so 1 plus 1, 1 plus 1. So the hydrogen form 1 covalent bond. The nitrogen being 5 outer shell electrons because it's in group 5 would like to gain 3 valence electrons, but then because this is bonding with non-metal atom, therefore it's not ionic bonding. Therefore you do not just transfer the electrons and gain the electron from the metal atom that will lose the electrons. Here instead you do sharing of electrons and form covalent bonds. So it has to share and obtain 3 extra electrons from the other hydrogen which it share electron with, and therefore it forms 3 covalent bonds here, which in this case is 3 single covalent bond. I'll just jump straight to nitrogen molecule. So this is a nitrogen molecule. The nitrogen that we have in the air exists as this diatomic molecule. So just like oxygen before, it consists of 2 atoms that are the same. These 2 atoms are the same, and because there's only one type of atoms in this molecule, this is also an element. So this molecule is an element, as you would know from concept about element, compound, and mixture, because it only contains one type of atoms. Despite it having 2 atoms in the molecule, both atoms are exactly the same. Again, previously as mentioned, group 5 for the nitrogen, so 5 outer shell electrons. Look at the cross, 1, 2, 3, 4, 5. Look at the dot, 1, 2, 3, 4, 5. Why do they form a triple bond? Because nitrogen is in group 5, so it's got 5 valence electron. The syllabus clearly states in atomic structure, group number tells you the number of valence electrons, and we know that atoms either want to gain electron or lose electrons or share electrons in order to obtain or achieve noble gas configuration. So 5 going to 8 is better than 5 losing 5. So 5 going to 8 would involve you gaining 3, but we only involve sharing of electrons because they are bonding between two atoms. They are the non-metals, and therefore they form triple covalent bonds, which is a triple bond between the nitrogen and nitrogen. That is 3 times covalent bond. Okay, 3 times covalent bond. It so happened to be between the same atoms, therefore it's called a triple bond, whereas this one is 3 times single bond. Okay, of course the other combination will be one single and one double. There will be 1 plus 2, which is 3 covalent bond as well. All right, so going to the next example, which is ethene. Ethene is an important organic compound, and you will learn more of this in organic chemistry towards the end of your O-level or IGCSE chemistry. So carbon form 4 covalent bond. This is a really important concept. Carbon form 4 covalent bond, because I don't know if it's stated previously. No, it's not stated. So I'll just show you one other thing. This is called methane. Methane is actually in your syllabus. This is CH4. Carbon form 4 covalent bond. Carbon is in group 4. Therefore, it's got 4 valence electrons. It is doing sharing of electrons because it's forming the chemical bond between non-metal and non-metal. So non-metal and non-metal form covalent bond. And covalent bond, as you know, is the electrostatic force attraction, blah, 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 as a result of sharing of electrons. Okay, so in terms of sharing of electrons, 4 plus something will give you 8 valence electrons around the carbon. That something has to be 4, and that's why carbon form 4 covalent bond. If you learn nothing from this lecture tutorial, you gotta learn something about this carbon, because carbon is present in every single life form, and carbon is the essence of organic chemistry. So when you do organic chemistry, which is the chemistry of life, carbon is everywhere. All right, so carbon forms 4 covalent bonds maximum. So I'm not saying that it cannot form lesser than 4 covalent bond, but it forms 4 covalent bond maximum, and that is a very, very important concept, because of 4 plus 4 giving you 8, which is 8 electrons in the second shell, okay, of carbon, which is being the central atom. 8 electrons in the second shell would mean a completely filled outer shell, which is the second shell, which would mean achieving a noble gas configuration. In the case of CO2 molecule, as well as ethene here, you see the carbon here, 1, 2, 3, 4. This carbon form 4 covalent bonds. If you look at this carbon, 1, 2, 3, 4. This carbon form 4 covalent bond. This is a double and 2 single. This is a double and 2 single. So you draw a double. Double bond represents 4 electrons, because 1 covalent bond represents 2 electrons being shared, 1 from each carbon. And they have in fact mixed in the dot and the cross. They're just using cross here for hydrogen, dot for this carbon, dot for this carbon, cross for this carbon, cross for this carbon, dot for this hydrogen. All right, so dot and cross diagram, you just need to differentiate where the electrons are coming from. Sometimes people will use dot, cross, and a triangle. Okay, but it's really up to you. I mean, they're all electrons. It's just to try and distinguish they're different, and 1 electron comes from each of the atom when they form this type of covalent bond. Lastly, we have this carbon dioxide. So carbon dioxide is a compound because it consists of 2 different elements chemically combined together in a fixed ratio: 1 carbon, 2 oxygen. All right, so it's also a molecule because it consists of 2 or more atoms bonded together. All right, so carbon here forms 4 covalent bond. Again, before I do the dot and cross, I will always try and draw the displayed formula. From the display formula, I can count the bond easily. 1, 2, 3, 4. Carbon form 4 covalent bond. Carbon is happy. There is no unpaired electron. There is no electrons that are not used for bonding on the carbon. The oxygen is in group 6. It's got 6 valence electrons. It will like to share, okay, 2 extra electrons with another non-metal atom, and therefore it would form 2 covalent bond maximum. So oxygen here form 1, 2 covalent bond. This oxygen here form 1, 2 covalent bond. So this oxygen is happy. This oxygen is happy. Oxygen is in group 6. All right, so 6 plus 2 giving you 8. 6 plus 2 giving you 8. This is in group 4. So 4 outer shell electrons plus 1, 2, 3, 4 being shared. 4 plus 4 giving you 8. Each of these is a second period element. In the second period, you mean you're filling in the second shell of the atomic structure, and that can allow a maximum of 8 electrons in the second shell, and therefore a completely filled second shell has 8 electrons. That will have the electronic configuration of a noble gas, which is neon, which is unreactive electronic configuration because it's completely filled second shell. Okay, so on the oxygen, don't forget that you only use 2 of its 6 valence electron for forming covalent bond, for forming 2 covalent bonds, and therefore 6 minus 2, you still have 2 lone pairs. Okay, so on each oxygen still have 4 non-bonding electrons. 4 non-bonding electrons. If you have 4 non-bonding electrons, they're always drawn as a pair to make it easier to count. So you have 2 lone pairs of electrons on this oxygen, but you also have another 2 lone pairs of electrons there. So altogether you have 1, 2, 3, 4. So CO2 has 4 lone pair of electrons. That is a pair of electrons. They are not used for bonding. So meaning to say 4 times 2 is 8. There are 8 electrons that have not been used for bonding in the outermost shell. All right.